Hello, everyone. My name is Terry Erzman. I'm the Chief Marketing Officer for Percona. Welcome to today's webinar. Before we get started, can I have a show of hands? If you can hear me, would you please raise your hand in the GoToWebinar control panel? Great. See lots of raised hands. Appreciate that. We are making a recording of today's webinar, and we'll post the recording as well as the slides from today, and we will send out an email with the details on where you can find those within the next 24 hours. If you have questions during today's webinar, please enter those in the questions box in the GoToWebinar screen, and we'll make sure that we answer as many as we can during the webinar, and if there are additional questions that come up, our presenter today will make a blog post on the MySQL Performance blog and answer any additional questions that need to be addressed. With that, I am pleased to introduce Bill Karwin. Bill is a principal consultant with Percona, and today's topic is tools and techniques for index design. Bill?
Thanks, Terry. Welcome, everybody. I'm going to be talking today about index design. This is a very popular subject and a very common one that needs to be addressed both for beginning users and for advanced users, because there's almost no end to the depth that you can go into this topic. Ultimately, it's about performance. This is an area in which we frequently find that as we do performance audits at Percona in our consulting services, we find that this is one of the most frequent topics that need to be adjusted in MySQL instances for the sake of performance. The good news about index design is that this is a great way to speed up your SQL queries and overall reduce the database load without actually changing any of your application code. So you can do this completely independently and transparently, and without having to restructure schema changes in many cases. And by schema changes, I mean things like restructuring your tables and changing columns and tables and so on. You could consider adding and dropping indexes to be schema changes, but for purposes of logical schema changes, that's what I mean. And yet, despite the fact that this is such a common issue and such an easy way to speed up your MySQL instance, this seems to be a neglected part of database development and maintenance, and I'll talk about how both of those come into play. First, I want to talk about some of the misconceptions that I hear a lot. I've been using MySQL since about 2000. I've been supporting databases since many years before that, and answering lots of questions online. I also do training for Percona for our live MySQL training, and I hear this quite a lot, some of these types of misconceptions. One I call index shotgun. That is, people think that indexes are a good way to improve performance, and more improvement of performance is better, right? So their solution, without having done much analysis, is to put an index on every single column. When I phrase it like this, it may seem a little naive, but I'm surprised at how frequently I actually see this in production sites or talk to people who do this. What's wrong with that? The indexes that you create, many of them are never needed. Only certain queries will use certain indexes. I'll talk about how. But the indexes that you create that are superfluous, that are on columns that never need to be indexed, are just adding to overhead. They occupy some disk space to store the sorted index data structure, and they also occupy memory buffers if they are used even seldom. They can occupy part of your key cache or your InnoDB buffer pool. The other overhead for indexes is that they need to be updated every time you change the data for the underlying table and insert an update, a delete. This adds to the overhead of adding and deleting values in that index data structure. The more indexes you have, the more overhead. It also makes the job more complex for the MySQL query optimizer, because if it needs to decide between 16 or 20 indexes on a given table, it will have a harder time to make that choice and deliver that optimization plan for a given query. So it just adds to some of the computational work as well as the storage and the memory usage. So with all this extra cost and overhead, some people become averse to using indexes, that they were told that indexes are costly to maintain, and so they don't create enough indexes. They may even create 0 indexes. I have seen sites that do this. They did so for the specific reason that they were trying to make things faster, and they were told in some resource or some article that indexes decrease performance in the cases of insert, update, and delete. What's the problem with that? Well, we need indexes for the queries that make use of them. Not only read queries, select, but also anything with a where clause can use an index, the update and delete statements as well. However, most workloads tend to favor the select statements. They're read heavy, and the ultimate benefit of using indexes to improve those queries is going to give you benefit in more cases than the cases that you have overhead. So the net is actually in favor of using indexes if the indexes are defined in the right way so that they are benefiting the queries that you run. It's also a better use of your memory to store indexes because they, by being sorted and being a more compact data structure than the table rows themselves, they are a more effective way of using memory. So memory is still expensive relative to storage, and we want to make sure that we want to have the best part of your database in memory at all times. What about SQL aversion? Some people are favoring moving to no SQL technology or non-relational technology, and the buzzword or the catchphrase is that it just works. However, in most of these technologies, NoSQL, they also have the concept of creating indexes. And in some ways, the process of deciding on the design for the best indexes is exactly the same as it is in an SQL database. They do require you to know which cases you need to create indexes for and to define indexes explicitly as a separate step so that they can speed up the queries later on. And I'm speaking generally. I think that there are some NoSQL source technologies that do indexing implicitly. Things like Solr or full-text search engines come to mind. But the other point I wanted to make about this is that few people realize that indexes are not actually part of the SQL standard. The SQL standard talks about the language, but not about storage or optimization. So the whole concept of indexes, the syntax of the create index statement, all the behavior is totally up to each implementation vendor. And so if you want to be cool and jump on the bandwagon for NoSQL, you can do so by just using indexes. Another question that comes up that I see is people post a diagram or a script describing their entire schema, and they ask, what are the indexes that I need to define for this schema? This is a screen capture I got from the Gene Ontology Consortium. It was just a good example of a complex schema that one could look at and say, I want to understand what are the best columns to index over this entire schema. The choice of indexes at a high level, we can say that it is derived from what tables and columns you need to query, not the structure of the database tables and columns. For example, what joins you need to perform, or what sorting or grouping by, what columns that you have in where clauses for search criteria. Those are all based on the queries, not the table design. So I say, and this is an important point that I want to make, is that index design does not derive from and is not implicit from table design. I want to emphasize that. This is lesson number one for what you need to keep in mind with index design techniques. Relational database schema design follows some rules called rules of normalization, and that describes how you should structure your tables and columns based on what the relationship is between data and what facts you're trying to store and so on. There are some pretty rigorous rules about the best way to do that to reduce the redundant storage and to make sure that you don't store information more than once. But the rules for creating indexes are not based on the data and the data relationships. They're based more on the queries that you need to run. That's the distinction that I see a lot of people, developers and database administrators alike, make a mistake on. They, when I phrase it like this, they kind of understand what I mean, and in retrospect it makes sense with their experience. But this is a distinction that I want to really call out. So if we have the requirement that index design derives from queries, what are our queries? We can find queries on a MySQL instance in a number of places. Here's a list. The slow query log is the one that I go to first. This is a log that exists on a MySQL instance that records all the queries that you are executing against that instance from any application they take longer than a certain number of seconds. You can change that threshold, so you can log more queries or fewer queries. You can even set the threshold down to 0, so any query that takes more than 0 seconds or more will be added to that log. The general query log is also a useful repository of queries that are running against that server. But the difference between the general query log and the slow query log is that the slow query log includes a lot of statistics about how long it took to execute a given query. The general query log doesn't have any of that information. It essentially has a list of every query that has run, but no timing information. You could log in your application. You could wrap every call to an SQL query in part of your application code, which writes it out to a log file of your creation. And a lot of people do this. Sometimes even frameworks that you may use have a facility for turning on and off query logging. This can be useful because it measures something a little bit more time-wise than the database server can measure. It measures the round-trip time, which only the application layer can know about. That is, if there's some delay that is incurred by the fact that there's network latency or delay, or if something else is going on that makes the database not see the fact that it's taking an extra few milliseconds to deliver the result to the application. This is something that you can record in the application itself. Application logging also has an advantage in that you can denote that a number of queries were actually run to satisfy a given page request. If you have only database level logging, you would only know that a number of queries ran. You wouldn't know exactly which page requests invoked them. TCP dump is a tool that exists on POSIX and Linux systems that allows you to actually capture the Ethernet packets on the TCP/IP channel and log them to a file. And we can use that information to capture the traffic between applications and database server in case we don't want to use any of the other logging methods. I also have on this list binary log and process lists. Those are a couple of other options that we have to get queries that are running, but they have limitations. The binary log doesn't include any select statements. It only includes statements that are modifying data or modifying schema. So insert, update, delete, create, alter, drop, a few others. So it's going to give an incomplete list of the activity on that database. The process list, we can always get a list of queries that are running at a given instant in time, but that is subject to being very inaccurate because we can, even if we poll that 10 times a second, we may be missing a lot of queries that are so quick that they're falling in between the polling interval. So it's not a very accurate way of getting a set of queries that are running against your MySQL instance. My favorite is the slow query log. You can enable the slow query log with a set global command if it isn't already enabled. And this applies to any connection across your whole MySQL instance that begins after you enable this setting. I mentioned a moment ago that you can change the threshold of how many queries are added to this log. You can even set the long query time variable down to 0. So any query that takes 0 or more seconds, that is essentially all of them, is going to be included in the query log. Percona Server has some additional features. That is, we have determined that there's more information that the server has available internally that could be added to that log. So we have added a feature, log slow verbosity. There's a few different options for this one, but I just set that to full, so it enables all of the optional subsets of enhanced information to that slow log. How do we use this slow log? Percona Toolkit has a tool called PT Query Digest. And this is a script that will read your slow query log and give you a report. We can use this, here's an example on this slide. The very basic instructions for using it is to run this at the shell prompt with an argument of the file name of your MySQL slow log. Typically, by default, this is under the data directory for MySQL. So in this example, I'm showing the default path name to that. You can also copy your slow log anywhere else and process it there. In fact, I find that it's useful to copy it to another server, so whatever work that the PT Query Digest tool is doing to process it doesn't interfere with the load on your production database server. So my habit is just rsync or CP the slow log to another server that I know is not going to be burdened if I run a statistical analysis on the log. Because logs can be big. They can be megabytes or even gigabytes in size, and that could take a lot of computation. And I have had that interfere with the production traffic. And in this example, I'm just capturing the report to a small file called pqd.txt. Of course, you can call that anything you want. The idea of the PT Query Digest tool is to give you a report of the queries that are accounting for the greatest load on your database server. And it will give you a ranked list. I'm going to show you just a subset of the report. There's more to this report that we could go into, but the focus today is on utilizing this to identify which queries need to be attended to in terms of optimizing. Here's an example where it shows a ranked list of the top 10 queries that are running on a given instance. It will show them to you in descending order by the total aggregate response time. So you can see on the top query there is taking 28.8% of total response time on this database instance. The number of calls to that particular query type are few. It's only been called 78 times, but each time we call that query, it's taking over 60 seconds to execute, versus some other query that is also in the top 10, which is individually, the query is very quick, but it's called so frequently that it actually accounts for at least 4.5% of the aggregate time on the database instance. This ranked list is important because it gives you a very quick way of seeing which queries are your heavy hitters, the ones that need optimizing most urgently. You would naturally want to attend to the queries that are the highest in this list, because if you can speed them up even by a fraction of a percentage of what they're currently running, that would be much better than a much more aggressive optimization to a query that is way down on the list. It would give you better bang for your buck and the time spent that you do optimizing. The next technique that I wanted to cover is to rate the indexes that you want to create to help optimize a given query. and I'm going to introduce the star system. This is borrowed from a really good book called Relational Database Index Design and the Optimizers from 2005. It's a fairly up-to-date book. It goes into great depth on both physical and logical optimization for indexes, but I'm going to give you some of the short list of some of the techniques that are covered in this book. So the star system involves characterizing indexes with respect to a given query. So this, again, queries determine what indexes that you want to define, and we can assess whether an index is the perfect index for a query by describing these stars. The first star is earned by an index if the index helps to group the rows referenced by the query and minimizes the slice of the index that you need to read through. That is, I want to see just the rows that are matching my query criteria. I don't want to have to scan through others. So it's best if the index is able to narrow down my search most effectively. The second star is to help me get my query results back in the sort order that I want it in. So given that I've found the rows that match my query criteria, I may want to also order them. And an index that helps you do that earns the second star. The third star is also called a covering index. Some people call this an index-only query. This is earned by a query, by an index that allows all columns referenced by the query to be retrieved from the index itself. My analogy that I frequently use is to a telephone book. I can look up somebody by their last name and first name, and then those are my search criteria, but what I'm really trying to retrieve there is their phone number in that telephone book entry. So that would be an extra column that is not part of the searching that I'm doing, and it's not in any particular order, but it would be an extra column that I'm actually retrieving, and therefore I'm able to get that from the index itself. The purpose of that is to avoid having to read an entry in the index and then follow some pointer to seek around in the data file and read a row out of the table. That's the point of a covering index. So let me go into a little bit more detail about these. Here's an example query that has a where clause and an order by and a couple of other columns mentioned in the select list. The first star is allows us to identify the columns in the where clause. Those are columns that are involved in equality comparisons. So we have movie ID equals 91280 and role ID equals 1. Those are equality comparisons. So those are the ones that we look at first to define an index in the leftmost part of the index. So columns movie ID and role ID belong in our index. This will allow the query to pinpoint just the matching rows most efficiently if we have both of these columns in the index. Next, we also see that there's an order by with mentioning another column and our order in this example query. If we can think of this logically, once we have selected the slice of the index that has a given value for the movie ID and a given value for the role ID, we know that all the values, all the rows in that subset of the index are essentially tied. They all have the same value, 91280 and 1 for those two columns. So the order that we want to get them back is, it would be most helpful if they are stored in that natural order in the index. And by the nature of an index, given the distinct values of the first two columns of particular values, the rows will be stored in the order by the next column in the index. So we want to add that column to the index, and therefore the optimizer of MySQL will know that all it has to do is fetch back the rows in the order corresponding to the entries in the index, and they will be already sorted in the order that we've requested by that order by. This is a nice trick. and it can avoid the extra work that it would have to do during a query to sort the result set before it returns it to your application. We've basically already done the work earlier as the data was inserted into that index to sort it in the manner that we want to retrieve it, and so that step can be skipped. That's an important optimization. The third star involves the other columns. You see a couple of columns in the select list that are not mentioned either in the where clause or in the sort order. And these can be also added to the appended to the end of that index, so we get those as additional discrete items that we can retrieve from the index and avoid the need to actually read those columns out of the table itself. If they already come along for the ride as an entry in the index, we can avoid that extra work. And that's called the covering index effect. That can be a profound optimization and can avoid a lot of extraneous seeking around in the database that the query optimizer would otherwise have to do to fetch the columns for a given row. If we use explain, which is the primary command in MySQL to show us some insight as to what the optimizer is doing for deciding on what indexes to use, we can see evidence of these three stars. The first one shows us that MySQL has chosen the key on that movie ID column. The compound key is by default named after the first column in the sequence of columns we mentioned. So that's the index it's going to use. It's managed to reduce down the number of rows it's got to scan to 57 in this case. The rows field shows us that it's only estimated, it's guessing. It's not a very accurate number, but this is its estimate for how many rows it thinks it's going to have to read in order to produce this result set. So it's a very effective way of reducing down the set of rows that are matching. The number 2 star, we see that we are missing the usual comment in the extra field that you would say using file sort. Using file sort, if it were present, would tell us that MySQL has to retain an unsorted result set and then sort it by hand at the time that we execute the query. By that being missing, we know that it's actually benefiting from the index to get rows in their stored order, which is matching the order that we're requesting them in the query. And the third star is the covering index. And the sign that we are achieving that is this phrase using index in the extra field. That means it is able to retrieve the entire result set using the index without having to go back to the table itself. So there's our 3 stars. The full story is a little bit more complicated than that. There are cases when you can't achieve one or more of these stars. For example, in MySQL, frequently only one index at a time is used for a given query. So if you have more complex expressions in your where clause, you can easily get into a situation where there's no way for it to easily use a single index to satisfy that search. Frequently, just the use of an or expression or disjunction, logical disjunction, in a where clause can spoil the benefit of that index. Either you're looking for shoes that are blue or shoes that are in a given style in your product catalog for shoes. And you're referencing 2 different columns that are in, each of them have different orders. There may be an index on both of those, but it can only choose one index at a time, so it can't get both of those benefiting from an indexable search at the same time. So that's a problem. The benefit of that first star index is usually only helpful if we have AND expressions. So if we're applying those different columns to different fields in a compound index, that plays really well with the first star indexing. Second star indexes can be complicated by the fact that we may have conditions in our where clause that are not equality. We can have greater than, less than, not equal to, not in, between, like. Those predicates all match or potentially match multiple values in the index. And the complication there is that once we have had a range predicate like that is going to match multiple values, it kind of spoils any further use of the subsequent columns in that index, even if the index defines additional columns. As soon as we hit one of those range predicates on a column, we may not be able to benefit from the other columns in the index. Another case is where we're trying to both group by and order by in a single query, and you're referencing different columns. So the sort order that it's expecting to sort by in the result set is different from the criteria that we're grouping by, and that can be complicated and prevent us from achieving a second star index. And likewise, if we are accessing the rows in a different order than the sort order that we want, and I'll show an example of that in a moment. Third star indexes, the ones that allow us to get the covering index effect, are possible only if we can get the full value of the indexed field from the index. So for example, if we have a query that is fetching 60 columns from a table, a very, very wide result set, that can spoil the third star index in some cases, because there's a limitation in MySQL that you can only define an index with at most 16 columns. If you're fetching more columns from a given table than 16, then there's no way to create an index that contains them all. Likewise, we need to fetch the full column when we do. So any column that is larger than that which can be put into an index is also going to spoil our use of the third star index concept. We can't get the full string from a blob text or a long varchar if we can't fit that the full string into the index field. MySQL has a maximum of 1,000 bytes for an index over all the columns that are mentioned in the index. And keep in mind that multi-byte character sets account toward this as multiple bytes per character. UTF-8 is 3, and there's a UTF-8 extension for 4 bytes per character that is going to count 4 bytes per character. So let me show you another example query and how we would find indexes to benefit this. Here's an imaginary database or toy database that records movies and actors. It's actually based on IMDb. They do a public domain data dump that they offer. So borrowing that, I have a query that matches up character names with a many-to-many intersection table, and then finally to the actor's name. I'm looking for any actor who played James Bond in any movie, and then sorting by the name that comes back from that. What do we see when we do an explain on this query? We see some pretty bad optimization. So the first table for the character name is going to actually scan through 2.4 million rows and match that up looking through the intersection table, which has 21 million rows. And ultimately, one of the tips we have about interpreting this explain output is to just multiply those numbers of rows together, and that tells us how many row comparisons it has to do to evaluate the join. In spite of the fact that it can actually read that intersection table with the using index optimization, it can't do it all in one go because it's just much too long to do in one pass. So it has to do this in multiple passes using what's called the join buffer. This results in 52 trillion comparisons. And this is an artificial example, but I actually had an example like this a few months ago with a customer who said they had a query that was very similar. It was passing through an intersection table in a many-to-many relationship, and it had been running all weekend and showed no signs of finishing. So they were asking for some help on getting that optimized. What can we do to optimize this? Well, we can add a index on the character name so that we can look up the James Bond character more quickly. Notice that I'm using a prefix index for that, so it's not going to be able to be a third star index for that table because the prefix index is only going to index the first 20 characters of that string. It can't guarantee that it's going to retrieve the entire string length back from the index only, so it's got to read the or potentially read the data rows in addition to that. First star index, but it doesn't qualify as a third star index. The third star index on the other table, cast info, is a compound index that is very common for a many-to-many intersection table. And this allows us to look up the role ID, that is the rows corresponding to James Bond. Once we find the James Bond entry in the character name table, we can look up those corresponding rows in the cast info by the foreign key person role ID. This is a third star index because we also get, as coming along for the ride, the other column, which is the column that refers to the actor who plays James Bond. It's the person ID. And that column can be used to then retrieve by primary key the corresponding rows in the name table, the table that contains the actors. And now when we do an explain on it again to see how that works with these indexes, the same exact query, that's why I'm not showing the query here, we see that it's able to find James Bond as a single lookup, so it's found one row, and then from that it is able to look up a much reduced subset of the table in the intersection, and then finally for each one of those matches find a single entry in the last table, the actors. So we've improved this, at least in terms of how many comparisons that it needs to run through, by a factor of 480 million, which is a pretty good day's work done. That shows the power of both the first star and the third star indexes that is able to improve that to such a degree. And we wouldn't know unless we had done the explain plan. We had used our technique of deciding on the first stars and third star indexes, and then measured again with explain to see what the difference was after we did that. That's one of the things we emphasize at Percona is don't guess. Try to use whatever commands you have to measure and to get both predictive and measurement information about how the optimizer is going to work and how the query actually runs. In the case where I had a customer who had a similar type of query, their query had been running all weekend, we added an index in a very similar way, just a single index on the intersection table, and it made their 72-hour query finish in about 2 minutes, which is a pretty good improvement. And actually, when I say 72 hours, it wasn't even done, so we don't know how long it would have taken. Why couldn't I get a second star index in this example? The reason is that we're sorting by the actor name, which is going to be a sort order which is independent from the order that we're actually accessing the rows. We're accessing the rows through that join, through that intersection table, to the ID, so the numeric ID of the actor table, which is in a completely different order numerically than the alphabetical order of the names of the actors. We can't rely on the natural access order of how we're retrieving those rows to be the same as the alphabetical order of the column that we want to sort by. So we're stuck. This is a case where the best indexes that we can find are not able to achieve all 3 stars. And that's not uncommon. You shouldn't feel like there's anything you're missing if you can't get all 3 stars for every query. That's actually pretty common. The next is tidy up indexes you don't need. This is lesson number 3. What do you mean indexes I don't need? Well, basically I mean do create indexes that help your queries. Don't be averse to creating indexes just because somebody told you that they have some overhead to them. But once you do that, make sure that you don't create indexes, or in fact drop indexes that were created that aren't helping your queries. And you can get some information about that. A couple of other tools in the Percona toolkit can help. One is PT Duplicate Key Checker. MySQL doesn't prevent you from creating indexes that are actually redundant with each other. I'll show you an example. In this very simple example, we have a table, a couple of columns, A and B, and I create an index on A, I create an index on B, and then a third index on A, comma B. I run Duplicate Key Checker to analyze this, and it has output that looks like this. It identifies these two indexes, the one on a single column A and the index on the pair of columns A, B, and it reasons any query that could benefit from the first index could just as easily benefit from the second index. So there's really no need to have the first index in the database. It's just an extra index, takes more storage, takes more memory, takes more overhead for updating. You could drop that. And the output of this report from Duplicate Key Checker actually contains the alter table statement that would be necessary to drop the index that it's recommending you drop. Definitely review this report and make sure you agree with its conclusions, but then you can very conveniently cut and paste, or even just take this entire report and pipe it into the MySQL client to execute these alters. Notice all the other lines are commented out, so they can be ignored, and you can simply use this as an SQL script to run the alters that it recommends. But do review it first. You don't want to make these changes happen without you being aware of what's going on. Index usage. We may have also indexes that are defined and they're not redundant, but they are nevertheless not useful to any of the queries that we actually run. And index usage can analyze your query log. It will run explain for you on every single query in there and determine what indexes are used. It then compares that list of indexes that were used to the full set of indexes over your entire database. And those that are never referenced by any query, it recommends to drop. So it's a fairly simple thing. You could probably do yourself if you had many, many hours to spend doing it, but this is a nice script that does everything for you in a batch mode. Again, review the recommendations, because you aren't necessarily going to agree with them all. It's only as good as the completeness of your log as well. You may have queries that are only run nightly, and if your log is collected during the daytime, it wouldn't necessarily have queries that you actually need indexes for, and it may falsely conclude that it wants to drop some indexes. So yeah, exercise your judgment. You may know that certain indexes need to be kept despite the recommendation of this tool. In Percona Server, there's an additional feature that keeps track of which indexes and other objects as well are referenced ongoing, and it retains this in memory so that you can reference it later as information schema tables. The information schema.index statistics table tells you how many times it read rows benefiting with the assistance of a given index. You can turn this feature on. It actually has very little performance impact to just keep this on. It's described in this blog that I'm linking to. And then you can run a query comparing the index statistics to the table statistics, which lists every index in your MySQL instance, and output a list of those that it thinks have never been referenced by any query. And in this example, I'm doing so at the same time as formatting an alter table statement to drop those indexes. And that can be pretty useful. So this can be more accurate because it's actually measuring not the estimate that the explain would tell you, but the actual usage of the index and how frequently those are used at execute time instead of at optimized time. But it relies on using Percona Server to have this feature. And the last lesson I have is make this a habit. This analysis and reviewing the statistics deciding on what indexes are best, what indexes need to be dropped, has to be something that is a maintenance task that you do from time to time. So we're using PT Query Digest periodically. For example, when you push new code to your application, make sure that as you introduce new queries, you analyze the usage of them over time. The volume of your database can change which indexes are used, and also can make queries that were very quick early on become more expensive. And also your site traffic could change, so a given query could be run more frequently, whereas it used to be very rare. So all these are good reasons why it's good to run this periodically. I can even imagine setting up a cron jobs to run it weekly or more frequently. PT Query Digest has a lot of other options. For example, you can save the list of query types that it has previously reviewed to a table, and there you can actually make your own notes, entering information about what you did to review them, how well you were able to optimize it, maybe associate it with a bug tracking number in your ticket system to say, I, Bill Karwin, reviewed this bug on this date, and I created this index for it, so this index was useful for this query. Query Digest also has a review history feature that saves the performance measurements to a table so that you can do queries over time and make sure that you understand how the performance of a given query type is changing. Checking for duplicate keys periodically after you make schema changes can be useful because people don't necessarily know what indexes already count as in the database, and whether their new index makes that one redundant. The nice thing about duplicate key checker is you don't have to run it against your production system. You can do it against any development system because it's statically analyzing the schema, not the data. And also periodically run index usage so that you understand how the index usage is changing over time, especially if you change the queries in your application code. This could change the usage of indexes over time. So this is the 4 lessons that I wanted to convey, that the best practices and methods and tools that we can use. Identify your queries, because that's what determines the proper way to decide on what indexes are going to be needed. Use the star system to rate the indexes against the queries that you've identified. Tidy up by removing indexes that are no longer used or are redundant. And then establish a operational periodic process to go and review this over time. I wanted to also mention that we're going to have a training class. It's a brand new training offering from Percona that we're going to be holding as a live virtual training online. So you don't have to travel anywhere, and more importantly, I don't have to travel anywhere. That's going to be coming up at the end of October, October 29th to November 2nd. It's run for 5 days, 2 hours per day at 10 a.m. to 12 p.m. Pacific time. And you can read more about what's going to be covered in that class at this URL, store.percona.com/catalog.php, !category equals 17. This is a very exciting class. We're going to be going into very deep detail on using the PT Query Digest tool, interpreting results of it, using all the options that it has for filtering and customizing the reports, and using the query review and review history features that I mentioned a couple of slides back, and establishing ongoing policies and procedures for using that over time. And there'll be a lot of hands-on usage of that too, so you'll get some experience at running the commands yourself. We'll have some sample database that you can play with for that purpose. And I really invite anybody who is interested in that particular tool, the PT Query Digest, to join us for this training later on in October. So that's my presentation for today. thanks all for joining. Terry, do we have any questions that have come in?
Hello, everyone. Again, if you have some questions that you'd like to ask about today's materials, please submit them now into the questions box on your GoToWebinar control panel, and we'll answer as many of those as we have time to address.
I also posted a blog a couple of days ago on mysqlperformanceblog.com announcing this webinar, and if you think of other questions that you have that you'd like to follow up with, you can post those questions there, and I'd be glad to answer them on that blog.
Okay, Bill, we have a question. Does MySQL 5.6 change some of the rules to creating indexes?
Interesting question. I know that they've done some improvements to the optimizer in MySQL 5.6 to improve some of the cases where it's able to use indexes. I haven't studied specifically the types of optimizer changes and how that changes the usage of indexes, but the rules that I covered today, the star rules of characterizing how well indexes are able to be used, is still going to be quite relevant. That is, we want to treat indexes as a logical entity as well as a physical entity, and those rules are pretty much independent of implementation. The first star of deciding on what columns are indexable in your where clause, the second star of adding a column for the sort order, and the third star of getting covering indexes. Those techniques are going to still be relevant for 5.6.
Okay, next question. Are two-star order by indexes always irrelevant when using group by statements?
Not necessarily, because the sort order of your result set could match the criteria for your grouping. So if you're grouping by customer and you want to sort by customer, then it would be beneficial to have that second star index to benefit both the grouping and the sorting. But that's kind of a coincidental case. You're right that if you have different criteria for the grouping and the sorting, it's frequently the case that you cannot achieve a two-star index.
Okay, next question. Should you consider making two indexes if you believe the optimizer will choose to use an index merge?
Yeah, the index merge is an exception to the guideline that I mentioned earlier, that MySQL often, or in earlier versions of MySQL, can certainly only use one index per table per query. So the index merge allows you to have the benefit of two indexes in a given query be used, and it will use the union or the intersection of of both indexes. In cases where it's going to get the intersection, it actually turns out to be much more beneficial to actually define a compound index instead of relying on the merge of two single column indexes. And you can see that both in the, excuse me for the beeping, you can see that in both the rows mentioned in the explain plan and just empirically measure the performance of the query with a stopwatch, and you can see how that will actually be much more beneficial to have a single index that has multiple columns versus multiple indexes with a single column.
Okay, question. The question is, will you add a comment to your blog entry with the title of the book you mentioned? And I guess also can you mention the title of that book again?
Oh yeah, we'll definitely add a link in the blog for that, relational database index design and the optimizers, and I will be glad to make a link to that and also to a good review of that book that will help you. It wasn't a cheap book, but it's very, very valuable, and I recommend that one.
Okay, next question. Please explain the cube technique of that book you mentioned.
The cube technique, the quick upper bound estimate, is another technique that they go into for trying to analyze theoretically the cost of using an index. And that's a little bit beyond the scope of this presentation, but it's a more advanced technique for trying to get a more accurate measure of how much benefit an index is going to have for a given query. So I'm going to leave that to another day. Maybe we can do another webinar or another presentation about that.
Okay, very good. I've had a few questions here about the presentation today. So just to reiterate for everyone, we are recording today's webinar, and we'll post the recording as well as a copy of the slides to a web page, and we'll send out the URL for that page to everyone who registered for today's webinar here within the next 24 hours. With that, looks like we're about at the end of time. We have a few more questions that we didn't have a chance to address, but will probably be better covered in a blog post. So we'll forward those over to Bill, and he'll have a chance to review them and put together some follow-up information on today's webinar. With that, thanks everyone for attending today. Please keep your eye on our Percona.com/webinars page. We do offer webinars periodically. We're posting new webinars frequently, so please check back from time to time. Bill, thanks for today's webinar, and thanks to everyone for attending.
Thank you, Terry. And thanks,
Have
everyone.
a good day.